Hello friends, welcome to this session. In this session, we will study about the effective length of the column and related numericals on the Euler's formula that we have derived in the last video lectures, that Euler's formula. So we'll take one numericals also in this video lecture. So up till now, whatever the topics we have studied about the actually loaded columns, in that we have studied about the different types of the columns, simple short column, medium column and long columns, and also the different stresses are induced into these columns, and also the failure criteria of the different types of the columns also are important. And basically the short columns are failed due to crushing because of the compressive load. That is the major important factor for the failure of the short column. And for the long column, comparatively the long column is failed due to it is a buckling load, right? So that you have to remember. So obviously there are compressive loads are there, but that whatever the compressive stresses are induced, that compressive stresses are more, and most of the time that long column is failed due to buckling. Okay, so let us start to this video lecture, that is equivalent length and their numerical. First of all, the equivalent length. Here it is, a definition is written that the distance between the adjacent point of inflation or between two zero bending moment points is called as equivalent length, or it is also called as effective length of column. Means here do you understand that equivalent length is nothing but the distance between the two zero bending moment points. Okay, so basically we know that if it is a column is there, which are different types of the end conditions are there. In the last video lecture we have seen that various types of the end condition, that 4 different end conditions are there. If maybe both ends are fixed, both ends are hinge, one end is hinge, other end is free, one end is fixed, other end is free. So like that end conditions are there. And if you depending upon these end conditions, there are reaction components are also exist. And if you draw the bending moment diagram, and if you see that at the ends the zero bending moments are there, and if you find the distance between zero bending moment, or it is also called as a point of inflation, that length, it is called as equivalent length. Okay, so this is the definition of equivalent length. So first case, both ends are hinge. So equivalent length is equal to actual length if both ends are hinge. So that derivation part we have seen in the last video. So in there, that equivalent length, if the ends are hinge, at that time equivalent length is equal to actual length. Okay, so equivalent length is symbolically represented by LE, and actual length most of the time it is shown by L. So in that case both are equal, so LE is equal to L actual length, right? So second end condition is one end is fixed, other end is free. So in that, equivalent length is equal to 2 times of actual length. So here it is, make it correct that LE is equal to twice of L. Okay, so LE is equal to twice of L, that is equivalent length is double of the actual length, right? So third end condition is one end is fixed and other end is hinge or pin jointed or pin end. So equivalent length, here it is actual length divided by under root of 2. So we can also write LE is equal to L divided by under root of 2. So you have to remember, if it is the one end is fixed and other end is hinge, at the time equivalent length is actual length divided by root of 2. Next, both ends are fixed. In that case, your equivalent length is equal to half of the actual length. So here it is LE, or sometimes LEQ is equal to L by 2, or half of the actual length. And one note is there, that is effective length is the distance between 2 points of zero bending moments. Okay, so you try to remember that effective or equivalent length is the distance between 2 points of zero bending moment. Okay, so you have to measure the distance between the two zero bending moment points. So these are the different end conditions, and their effective lengths are calculated, and their relationship between the actual length and effective length for different end conditions. Here it is we have seen. So that will be helpful for solving the problem. In that case, in the formula, most of the time we have to use the effective length, and sometimes in the problem actual length is given. In that case, depending upon the end conditions, you can calculate the effective length, right? I hope you understood this. For different conditions, the relationship between the effective length and actual length. So here relation between the effective length and actual length is given. Effective length is symbolically represented by LE. Therefore crippling load. So this derivation we have seen in the last lecture. Crippling load in terms of effective length. So crippling load symbol is P is equal to pi square EI divided by LE square. Okay, so this derivation is we have derived for the when both the ends are hinge or pin. Okay, so in the tabular form you can see end conditions. First condition, both ends are hinge. That case relation between equivalent length and actual length both are equal. If you put that value in the above crippling load equation or Euler's equation, so here P is equal to pi square EI divided by L square. So instead of LE we have put L. So that's why the equation is same, because here equivalent length and actual length is same. Second case, if one end is fixed and other end is free, so we know that effective length is double of actual length or twice of actual length. So if you put that LE value, that is a twice L, in the above formula, so your formula becomes P is equal to pi square EI divided by 4L square. Third important case, that both ends are fixed. In that case, our effective length can be determined by half of the actual length. Okay, this we know that. So if you put that effective length value half of the actual length, means L by 2 into above the formula. So our formula will become pi square EI 4 divided by L square. If you put simply instead of LE, you simply put the L by 2. Fourth case or fourth end condition is one end is fixed and other end is hinge. In that case, effective length is equal to L by root 2. So if you put that LE value, means L by root 2, in the above crippling load formula, your crippling load P is equal to 2 pi square EI divided by L square. So if you simply knows the own formula, that is a crippling load, you can directly put the values depending upon the end conditions, and you can find the crippling load formula. Okay, so or other way you can determine as per the end conditions, you can remember the crippling load formulas for different cases. So let us take one small problem onto this. So I will read the problem. Calculate the safe compressive load on a hollow cast iron column, that is one end is rigidly fixed and other end is hinge, of 150 mm external diameter, 100 mm internal diameter and 10 meter length. Use Euler's formula with a factor of safety 5. Capital E, that is modulus of elasticity, is 95 giganewton per meter square. Okay, so this giganewton per meter square means it is a GPa, that is a gigapascal. Okay, so solution. So first of all, external diameter, internal diameter, or this hollow cast iron column is there. That's why there are two diameters are given. External diameter and internal diameter values are given. Length, actual length of the column is given. It is 10 meter, and we have to use the Euler's formula to finding out the safe compressive load. So first of all, we will start from the LE, that is effective length, as the one end is fixed and other end is hinged, that's why our effective length is equal to L divided by root 2. L is the actual length. In the problem it is given 10 meter, so you make it convert into mm by multiplying 1000, so we'll get 10,000, 10 meter to 10,000 mm. Okay, it's converted, divided by root 2. So if you do the calculation on the calculator, your value will getting 7071.06 mm. Okay, so this is the equivalent length or effective length of column. So P is equal to pi square EI divided by L square. This is our basic formula for crippling load. So crippling load we first determine by using this pi square. E value is given, elasticity, modulus of elasticity 95. So giganewton per meter square, it is converted into MPa by multiplying 10 raised to 3. So 95 into 10 raised to 3, you can see, multiply by I, that is I is the moment of inertia, or I minimum moment of inertia in that direction. So pi by 64 into d raised to 4 minus external diameter is 150 raised to 4 minus 100 raised to 4. Okay, so for a hollow circular column, I minimum, that is the moment of inertia, is pi by 64, capital D square, that is external diameter minus internal diameter raised to 4, and effective length we determine, that is a 7071.06. So now you just do the calculation and you can determine the value. That value, it is the crippling load. Okay, so that P is equal to 747.14 kilonewton. So this is a crippling load, but in the problem they ask about the safe compressive load. Safe compressive load. So safe compressive load, if you have to determine, you should know the factor of safety. Okay, so one term in the earlier slides we have seen that safe load can be determined by taking the crippling load and the factor of safety, the ratio. So here you can see the safe load is equal to P, that is a crippling load, divided by FOS, that is a factor of safety. We already determined the crippling load P, and the factor of safety is given already in the problem. So you can see here factor of safety is 5, it is given. Factor of safety is 5 is given. So only just simply you have to put the factor of safety and you can determine the value, that is a safe load. Okay, so this safe load is most of the time it is useful for the actual design of the column, whether that column is long, because Euler's formula is most probably for the long column which is subjected to buckling load. So here crippling load and their safe load also we have determined with the help of factor of safety. Okay, so this is a very small problem, and only one condition is considered here or given in the problem, that is a rigidly fixed and hinge. So depending upon if the end conditions are changed, so depending upon that your effective length value or equivalent length values are also changed. But the basic crippling load formula, this is same, and you have to just determine the other values, that is most of the time modulus of elasticity is given, and you have to determine, depending upon the section, minimum moment of inertia and the effective length, as you know that, depending upon the end conditions. And if it is they ask about the safe load, so by using the factor of safety you can also determine the safe load of the column. Okay, so I hope you understood this particular problem, and also the relationship between the effective length and equivalent length and actual length of column. Okay, so thank you very much.